Today we're going to look at how to take the limit of a given function. So first we're going to consider the function f of x equals x squared plus x minus 2 over 2x minus 2. So first let's consider the domain of this function. Since we have a rational function here, the main problem is that we don't want the denominator to equal 0. So the domain will be all real numbers x, except that we don't want 2x minus 2 to equal 0, which if we solve this, we get that x cannot equal 1. So 1 is not in the domain of our function. Our function isn't defined at that point. But what a limit does is we want to look what happens really close to 1. So what we're going to do is we're going to pick values of x that are close to 1, plug them into our function, and see what happens to the y values as x gets closer and closer to 1. So we'll start off with x being 0.9. And if we plug that into our function, just use your calculator, you get that f of x is 1.45. But then we can even get closer to 1 than that. Let's say x is 0.99. If we plug that in, we get that f of x is 1.495. But again, this process never stops. We can get as close to x equals 1 as we want by just getting closer and closer. So if we plug in 0.999, we get 0.4995, and let's do one more. So 0.999, we get 1.49995. We should also check on the other side of 1. So if we pick a number slightly bigger than 1, like say 1.1, and plug that in to our function, we get 1.55. But again, we can always pick a number closer than 1. So let's say 1.01. If we plug that in, our y value is 1.505. And we'll just do one more. So if we plug in x equals 1.001, we get 1.5005. So the idea here is that as x approaches 1, what happens to our y values? So as x approaches 1, as these numbers got closer and closer to 1, my f of x values got closer and closer, or approached the value of 1.5. So that is our limit here in this case. The notation that we use for this is the limit as x approaches 1 of f of x is equal to 1.5. We can see this graphically as well. We can see as the x values get closer and closer to 1, the y values get closer and closer to 1.5. And this also works on the coming from the right hand side. As x values get closer to 1, your y values get closer to 1.5. The link to the Desmos graph here will be in the video description below, so you can play around with it, try some different functions, try it at different points. For our next example, we have this piecewise function where f of x equals 1 plus x squared when x is less than 1, and 5 minus 2x when x is greater than or equal to 1. So the first thing that I want to point out is that x equals 1 is in the domain of our function here. In fact, we can really quick do this. F of 1 is 5 minus 2 times 1, which is equal to 3. So the function value at x equals 1 is 3, but since I'm trying to find the limit as x approaches 1, I don't care what happens exactly at 1, I just want to know what happens near 1. So again, we're going to construct a table of values to see what happens as x gets close to 1, not what happens at x is exactly 1. So we see as the x values are getting closer and closer to 1, the f of x values, or the y values, are getting closer and closer to 2. So it appears that this limit is equal to 2. But you always need to check both sides of the value that you're finding the limit at. So all of these values were less than 1, so we also need to see what happens on the other side when x is greater than 1. So now as we take values that are close to 1 but slightly bigger than 1, we see that as x gets closer and closer to the value of 1, our f of x values get closer to 3 instead of 2. So really, the limit here doesn't approach a single number. As your x values approach 1, your y values don't approach a single number. So we say that this value does not exist. And the shorthand that we'll use for that in here is that this limit dne does not exist. So again, this limit doesn't exist because as our x's approach 1, our f of x values don't approach a single number. It's often useful, though, with functions like these to talk about the one-sided limits, since it does seem that we have a limit, but they don't meet up in the middle. We can talk about the one-sided limits, the left-hand limit and the right-hand limit. The notation that we use for the left-hand limit is the limit as x approaches 1 from the left. So we put a little negative value there to show that we're approaching 1 from the left. So here, the limit as x approaches 1 from the left-hand side will equal 2, because as we saw, as the x values approach 1 from the left, our f of x values approached 2. And then for the right-hand limit, we use a positive sign. So we have the limit as x approaches 1 from the right of f of x, in this case, equals 3. Because as we took values of x that were slightly bigger than 1 but got closer to 1, the f of x values got closer to 3. We can also talk about taking infinite limits of a function. So here, instead of taking numbers that get closer and closer to some value a, we're going to take numbers that get closer and closer to infinity. So in other words, we want to take x values that get bigger and bigger. So if we draw our table here, so let's start with a big number but not too big, x equals 10. And if we plug that into this function here, we get the value 3.0902. And I'm rounding a little bit, but so let's go even bigger. So let's say x equals 100. If we plug that in, we get 3.1411. If I plug in x equals 1,000, I get 3.14159. And if I plug in 10,000, I'll write out until it stops following the pattern. We get 3.1415926, So, as we can see, as the x's get larger and larger and larger, so as the x's approach infinity, my f of x values get closer and closer to the value of pi. So we say that this limit here, the limit as x approaches infinity of x sine of pi over x, this limit equals pi, because the f of x values approach pi as we take bigger and bigger x values. So let's look at one more infinite limit here, the limit as x approaches infinity of cosine of x. So this time the values that I'm going to pick for x are just going to be integer multiples of pi. So I'm going to take pi, and then 2 pi, 3 pi, 4 pi, so on and so forth. So my x values are getting bigger and bigger and approaching infinity. So now I want to see what happens with the f of x values. So cosine of pi is equal to -1. Cosine of 2 pi is equal to 1. Cosine of 3 pi is -1. Cosine of 4 pi is 1. And this could continue oscillating back and forth as we continue to go off to infinity. So this is similar to the Thomson's lamp example that you saw in the last video, that as we approach infinity, my f of x values never approach a single value. They keep oscillating between -1 and 1, -1 and 1, so it's impossible to tell what happens in the end. When you reach infinity, your f of x values never approach a single number. So again, we say for that, when that happens, that this limit does not exist. So that is our introduction to finding the limit of a function. Remember that in the video description below there will be a couple of Desmos links where you can try some different functions and see what happens to the limit of those functions at various values.